Okay. You remember we were doing the lattice filter. One advantage of the lattice filter was that it was generating the backward prediction errors which form an orthogonal basis of the signal space. That is, if you have xn, xn minus 1 up to dot 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 xn minus p, by that backward prediction errors, you generate a basis for that space, for the space spanned by those elements, which is an orthogonal basis. Okay, so any external vector, that is d of n, I mean, if you want to estimate it, you simply have to project it along each of these backward prediction errors, compute the projection and sum. And what is the advantage was that if you want to increase the order, if you want to have one more element, say xn minus p minus 1, you simply find out the additional backward prediction error component by cascading, by appending one more stage to this, find out the new backward prediction error, find out the projection along that, add to the previous one. You don't have to redo the entire computation. That is the advantage, right? So that typically your suppose one particular stage is this. Suppose this E p minus 1 B n I think this will be K p minus 1 star, isn't it? Because I am starting at p minus 1th order. So, this component you have to multiply this by one factor. What is that factor? Inner product d n with E p B n divided by norm square of E p B n, that is sigma p b square. If you take this scalar, put a multiplier, that multiplier times this, that will be the projection of d n along this backward projection error. This you have to do for all the backward projection errors, find out the individual projections and add. Are you following me? d n has to be projected on E0 B n, E1 B n, E2 B n, dot 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 E p B n. All the projections have to be added. Then d n will be projected on the space spanned by xn to xn minus p. Okay, and you can go on adding more stages, so the space will go on expanding. You will have higher order projections also. So typically this is the projection coefficient. So naturally you have to find this also. Then only you can multiply E p B n by this, isn't it? You have to, but this coefficient is not difficult. This sigma p b square is already found out. In fact, it should be called sigma p square because sigma p b square and sigma p f square, they are same. And this is nothing but this d n, you write this way, E p B n means x n minus p minus the error, and error had, in fact it should be this way because these terms had minus sign, minus and minus plus, j was from 0 to p minus 1, I think so. J equal to 0 x n, j equal to p minus 1, x n minus p plus 1. Okay. B p p, B p 1. This is this, and you this correlation will be what? Instead of okay, earlier we gave a name p vector as the cross correlation vector between, consider the real case or not even real, say okay, consider this case, cross correlation vector between this and this, x n vector into d star n. Okay, but I have already used the notation p for indicating the order. So instead of p vector, you give a different name to it, you call it q vector, because I have already used up this symbol p once, so there is no, there might be a confusion. So what is this coefficient? d n with x n minus p, that will be actually q star, because the way definition is x n and d star n, that is q, and here you have d n with x n minus p. So actually you can put a thing and then put a star here. This will be q p This will be what? Qj, isn't it? Huh? Qj, xn minus j is component here, times d star n is the opposite here. So, Qj and star. So, if you know these terms, these coefficients you have already evaluated order recursively. So, you can find out these. Again, this is not for online computation, this is only for constructing the lattice. Once the lattice is constructed, these multipliers are stationary and fixed. Then you go on filtering xn, you get all the backward prediction error, forward prediction error, and the projection of dn and all those things. It is only offline computation, that is to compute these various parameters recursively, or even directly. Here it is direct, because once you find out these coefficients bp, comma anything recursively, then put them back here, carry out this overall correlation terms, summation of this correlation, that will define this inner product. Okay. This is just the formula. This is how to get these coefficients, because you must know these coefficients. You must know these coefficients. Then only you can carry out the projection. Okay. We will now see one another nice property. Actually, this property can be proved in various ways, but let me first consider it, prove it, discuss it, prove it, and then I will tell something more about it. Suppose I am doing linear prediction. There is a process, random signal xn, which is WSS, 0 mean say, and WSS, and there is really no linear relation involving the samples. So, no sample is a linear combination of the remaining ones, either finite ones or infinite ones, okay, which means any projection, if you take any xn projected on the space span by any other set of the samples, the projection error is always having, non-zero variance, there is non-zero norm square. Okay, this is the case we are considering. So, there, suppose I am considering a pth order prediction. So, pth order prediction means the prediction error, forward prediction. Prediction error according to us will be okay, because there is already a negative sign here in the coefficient, so minus and minus plus. And EPFN is orthogonal to what? W1 comma P. What is W1 comma P? That is span of isn't it? I am projecting xn orthogonally on the space span by xn minus 1 to xn minus p. I am taking the error. That error is orthogonal to the space. The space is W1p. So, this is this. Now, consider Z transform of both sides. So, what you get here is as Az into Xz, where Az is okay. So, Az is a polynomial in Z of what order? Pth order, isn't it? So, I can factorize into p first order factors. Some factor might repeat, but say p first order factors. The roots may be complex in general, but I can, by the fundamental theorem of algebra, as long as these coefficients are over complex fields, I can factorize it. As long as the coefficients are complex, or complex numbers are allowed, I can factorize it into p first order factors. So, consider one factor at a time, say q z inverse into remaining one is a prime z. Okay. You see, factors I can always write in this form, 1 plus or minus something into z inverse. Otherwise, if you want to do like a schoolboy, you convert everything as a power of z, then z minus a, z minus b, z minus c, again you can write in this kind of form. What is the point? you can write it this way, because after all the overall thing is a power series in Z inverse. So, 1 minus q Z inverse into A prime Z. So, A prime Z, its degree is, its order is p minus 1. One factor has been taken out. Huh? Why you call it Z inverse? Have I called it AZ? I called it JAZ. A prime Z also will be a polynomial in Z inverse, isn't it? But this is a polynomial in Z inverse. I took one factor out. This is also a polynomial in Z inverse. Leading coefficient will be 1 like this, isn't it? And its order will be p minus 1. Okay. So, this factorization of AZ into this form, it means what? I can cascade it like this. Call it yn, and this is your EPFN, isn't it? Cascade. The yn is a linear combination of what? This is a polynomial. You can call this polynomial A prime Z. If you want, I can write it explicitly. A prime Z is something 1 plus some A prime p comma I Z inverse I equal to 1 to p minus 1, right? Isn't it? Some new set of coefficients. So, that means yn with what? A linear combination of xn minus 1 up to xn minus p plus 1. Xn, that is past p minus 1 number of samples, because order is less down. It is not pth order, it is p minus 1th order, right. So, instead of yn, if I consider yn minus 1, then yn minus 1 is a linear combination of xn minus 1 up to xn minus p. So, that means yn minus 1 belongs to W1p, isn't it? Yn was a linear combination of xn to xn minus p plus 1, that is yn belongs to W0 comma p minus 1. So, yn minus 1, it belongs to W1 comma p, because yn minus 1 means it is a linear combination of xn minus 1, xn minus 2 dot 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 up to xn minus p. We are starting at xn minus 1, isn't it? So, that means this is true. So, that means EPFN, which is orthogonal to W1 comma p, EPFN is after all orthogonal. EPFN is what? Xn projected on this and the error. So, EPFN is orthogonal to yn minus 1 also. EPFN is orthogonal to yn minus 1, because yn minus 1 belongs to W1 comma p. It is a function of xn minus 1 to xn minus p, and this guy is orthogonal to each of them, be it xn minus 1, be it xn minus 2, be it xn minus p. Okay. That means what? Okay. Now, EPFN, the beauty is I have found it, yn instead of yn I made it yn minus 1. Immediately yn minus 1 was member of this, not yn is not a member of this, yn minus 1 is a member of this, and this EPFN is orthogonal to W1 comma p, not W0 comma p minus 1. EPFN is orthogonal to W1 comma p. So, these two I can connect, and immediately I can say EPFN is orthogonal to yn, yn minus 1. But at the same time EPFN is what? Yn pass through a filter like this. So, what is EPFN? Yn minus q into yn minus 1, simple FIR filter, first order, yn minus q into yn minus 1. That is simple DSP says EPFN is what? Yn minus q into Yn minus 1. That is from DSP. So, in this inner product which is 0, I replace EPFN by this expression. This EPFN is this. Geometrically, what is happening, you know? EPFN, it is orthogonal to this guy, Yn minus 1. This is q into Yn minus 1, together is Yn. Yn is summation of the two. EPFN orthogonal to EPFN is orthogonal to Yn minus 1, and therefore anything along Yn minus 1. This q into Yn minus 1 in EPFN added together is Yn. Okay. So, EPFN is orthogonal to this, but EPFN is Yn minus this. I have to finally, you know, write everything in terms of Yn rather than EPFN. That is what my journey, direction of movement is. So, EPFN you write as this means what? Yn with Yn minus 1, that is Ryy1. This implies what? Minus q into Ryy0. That is 0, that is this is equal to Ryy0. This is one relation that comes immediately from the orthogonality of this error with Yn minus 1. From this relationship, immediately, that this is orthogonal to this and summation of the two is this, immediately you get this. Okay. Now, norm square of EPFN, as I told you, no sample xn is a linear combination of its past or future samples. That is why EPFN is what? It is a projection error whose norm square or variance has to be non-zero, has to be positive, it cannot be 0. Our assumption is this is a full rank process, that is no sample is a linear combination of its finite number of past or infinite number of past or finite number of future, infinite number of future terms. There is no linear relation linking the elements, that one is a linear combination of the others. In such a case, and in this particular case, that means xn is not linearly related to xn is not lying in the space this. That is why xn projected on this and the error which is this, that is a non-zero, that is positive norm square. So, this which is equal to variance is strictly greater than 0, this we know, but this norm square means EPFN with itself 0. What happened? Sorry, greater than 0. Yeah, greater than 0. Thank you, greater than 0. And now there are various ways you can go about. EPFN you can write as Yn minus this. This you can write as Yn minus this, q Yn minus 1. EPFN is orthogonal to Yn minus 1, isn't it? That is, this dot product with itself means what? This dot product with this. That is what I am saying, because this is nothing but this plus this. This implies that is this EPFN you can always write as Yn minus q Yn minus 1, isn't it? And EPFN and q Yn minus 1, that inner product is 0. This fellow is 0. So, EPFN with Yn, that is greater than 0. Now, replace EPFN by this expression, EPFN by this expression, Yn minus q Yn minus 1 comma Yn greater than 0. This means, now you expand it, Yn with itself minus q what? Yn minus 1 is Yn, that is Ryy star 1 RYY, because yn minus 1 coming in the first coordinate, yn going in the second coordinate. Correlation would have been, I mean, RYY1 is inner product between yn and yn minus 1. Here it is the opposite, so conjugate. So this is q comes out, q times RYY star 1. This is greater than 0, right? But earlier I have found a relation between RYY1 and RYY0 using the orthogonality. So I replace RYY1 by this. That means RYY star 1 means q star into RYY 0. RYY 0 is always real. Star of RYY 1 is star of the entire thing, is product, but only q star, because RYY 0 is the variance, it is never complex. RYY 0 is the variance, non-square, inner product with itself, it is never complex. Please see this step. So this is, you understand? So I replace it. So RYY 0 remains as it is. So you get this term 1 minus q into q star. Okay or not? Now what does it mean? RYY 0. What is yn? Yn is here. Now again, yn is what? Xn plus a linear combination of xn minus 1 up to xn minus p plus 1. Yn can never be a 0 random variable. That is, it's not, that would mean xn is a linear combination of plus p minus 1 samples, isn't it? Yn variance, this is according to me, it's not only real, it is always greater than or equal to 0, but according to me this is greater than 0, because if it is equal to 0, that means it is a 0 random variable, it always takes 0 value, which means xn is a linear xn plus this xn and the linear combination of xn minus 1 to xn minus p plus 1, that is 0, that is xn is lying within the space spanned by xn minus 1 to xn minus p plus 1. That is again contradiction. I am assuming our sample, no sample is a linear combination of other samples. No sample belongs to the space spanned by its past or future samples. Okay. That means yn can never be a 0 random variable. Variance of yn has to be positive. Okay. So that means that implies mod q is less than 1, mod q square is less than 1. So mod q, mod has to be a positive number, mod q less than 1. What is the implication of this? That whenever you factorize this linear predictor polynomial, every root which is a 0, every 0 lies within unit circle. So remember, lattice had so many stages. At each stage we are computing the pth order prediction order polynomial. Next stage, p plus 1th order forward prediction polynomials. Each of these polynomials has zeros lying within unit circle. A polynomial whose zeros lie within unit circle is called minimum phase polynomial. Minimum phase. So understand it. Lattice is a cascade of stages, but each stage gives rise to a minimum phase predictor polynomial, forward predictor polynomial. Because in any stage what I am doing, I am finding out the pth order, say any stage, say pth stage. What I am doing? I am finding out the pth order forward prediction and the corresponding polynomial, those coefficients, a p comma I 1, 2, 3 up to p. Those coefficients, they give rise to the forward prediction polynomial, isn't it, in Z domain, and it's for any order p. So for every order, I am finding out the linear predictor prediction and therefore the predictor polynomial. But by this theory, every predictor polynomial is minimum phase, that is, has its zeros within unit circle. Okay. So if I construct a system by taking the reciprocal of this linear predictor polynomial, that will be causal and stable. These are zeros. Suppose I take that Az and make a system 1 by Az. So zeros become poles, but for that system poles lie within unit circle, isn't it? So that means there will be a causal and stable system that will be guaranteed.
Can we see this thing directly?
How?
I'm asking, is it possible, like we have derived this much to get such a nice thing?
You cannot.
So this should be visible somewhere in the vector space itself.
No, But there are other proofs. Now I tell you one thing, there are various proofs given to this property. When I studied this when I was a student, that time this proof did not come up. Actually, that time we used that property, that each reflection coefficient has magnitude less than 1. Using that, and there is some theorem from complex analysis called Rouse's theorem. They really found out the roots of, assuming that polynomials up to pth order are minimum phase, and then find out the polynomial for p plus 1th order by the recursive formula we used. Then you show that that also is minimum phase. That is how it was done. Okay, but then uses some theorem of whose proof I don't know. That is called Rouse's theorem, ROUCET, Rouse's theorem. But 4 or 5 years back, I was just seeing one journal. I mean, I just glanced through journals. So I don't know whether you know of this guy, P.P. Vaidyanathan. Now, P.P. actually to us is known as P.P. P.P. actually is not a person of this area. P.P. is a very famous person. He actually comes from Calcutta. He studied in Calcutta University and then moved to Caltech, moved to Santa Barbara, did PhD there, and is a celebrated faculty member at Caltech, very, very well known. But he worked primarily in filter banks. He is a key person of that area. You can say the fountainhead of all research of that area. But I don't know how, in what context he was teaching this thing. He wrote in that, he published one short paper in IEEE Signal Processing Letters, which caught my attention actually. It was in 1999 or something like that. And towards the end, in the end he wrote, that actually I never thought that I would publish this, I just derived it, but someone who is a father figure in linear prediction system is John McHall, John McHall, M-A-K-H-O-U-L, John McHall. John has suggested that he must publish this result, so he published. And I read that proof and it caught my fancy. I think it is beautiful. So then when I teach, I consider the linear prediction, orthogonality and all those things, and I prove. But there is no simple proof. If you can come across one, I'll let you, let me know, but there is no simple proof like that. Okay. Fine. So linear prediction polynomials are minimum phase polynomials. Okay. Now we will do something related to this, not prediction, but something which is related to this. Again, there is a lot of theory in this. Unfortunately, it is not a course on spectrum estimation, so I will not go into it, but just hear me out. If you consider random processes, say zero mean random processes, stationary or not even stationary, then this kind of processes can always be decomposed into two things as a summation of two different random processes. One is called purely deterministic component and another is called purely non-deterministic. Purely deterministic but still random, mind you. So purely deterministic is one where any sample can be predicted exactly without any error from its past, either finite number of past samples or infinite number of past samples, but absolutely predictable. So deterministic random process is actually the predictable component. These components are like this. Say consider a sinusoidal random process, sin omega t plus phi. Phi is random, so every time you measure it, phi changes, and therefore the waveform changes, it is random, but sinusoidal nature remains. So if you know its values over one period, any future period values can be predicted without any error because of the sinusoidal nature. So this is a random process which is predictable. This kind of process, if you see its power spectral density, it will be line, because sinusoidal things, if you take their Fourier transform, they become impulses. So similarly here also, if you take a sin omega t plus phi, find its autocorrelation function. Okay, assume it to be stationary. Actually, it will be stationary if you assume phi to be uniformly distributed over 0 to 2 pi, which is always made. An assumption always made in control communication signal processing. The random phase is uniformly distributed from 0 to 2 pi. Then you can show that sin omega t plus phi into sin omega t minus tau plus phi. If you take the product, take the expectation with respect to phi, that is multiplied by 1 by 2 pi, 0 to 2 pi, all those things, then it will be some sinusoidal component of that gap tau. So if you take its, so it is basically a function of tau lag, so it is stationary. If you take its Fourier transform, it will give obviously an impulse. Impulse means line. So this kind of processes are called as processes which are having line spectra. So that predictable component actually can be shown to be either a single line or is a combination of several lines. So in the spectra they give rise only to lines. It may not be a single sinusoid, it may be predictable, but it can be decomposed into some sinusoids, random sinusoid processes, each giving rise to a line in the spectra when they are stationary. Unless stationary, there is no point in calling spectra, because power spectrum or PSD works or is defined only when the process is stationary. We all know Rotoko is a function of only one lag variable. Okay, so that is the one style. But the other component, which is called the purely non-deterministic component, that interests us more, because that is the kind of random process we come across in life most often. Other one also comes across, but they are synthesized by us in radar and all, where generate sinusoidal pulses or some predetermined pulses. Only this phase is random or amplitude is random, or it comes back by reflection from an object, and when it comes back, amplitude changes, phase changes. So there the structure is controlled by me, sinusoidal structure, the sinusoidal nature of the process. So in those applications, this thing comes up, this predictable process, its property and all that. But otherwise, in communication especially, we come across random processes, noise, all those things. There is nothing predictable. So that is a non-deterministic random process. In general, any random process has two components. One is predictable part, another is purely non-deterministic part or non-predictable part. In the non-predictable part, it said there is such a one where any current sample x of n cannot be predicted exactly without any error from its entire past. Even if you predict, the prediction error will have a non-zero, that is finite or positive variance. It is called this thing, non-deterministic or unpredictable component. Now, in this course, we are dealing with purely non-deterministic processes. This decomposition actually is called old decomposition. Please read books, Olds decomposition. That is, given any random process, say Vn, you write it as Xn plus say Un. This is purely deterministic. This is giving rise to line spectra, purely so you have a spectra, general kind of spectra, no continuous spectra. Line means discrete. You can say line spectra or discrete spectra. Discrete has to be line only, and this is a continuous spectra. Okay. We will be considering only Xn. Further, this is not the end of the story. Xn can be written as what? As generated by, there is a process Hn is generated by some instead of Un, let me call it Yn, Xn plus Yn. Un I want to use here. It is generated by passing a white noise, white sequence through a system which is causal stable. The causal stable linear time invariant system of impulse response Hn. Un pass through this, give rise to Xn. This Hn, so that means if you know h e to the power j omega, you know the power spectral density of Xn easily. It is some constant with the variance of this times mod h e to the power j omega square. This is the starting point of one very, very powerful method of spectral estimation called parametric method or method of modeling. That is, you assume the system to be, you know the system is purely non-deterministic, so you can model as though it is generated by passing a white sequence of some variance through a LTI system that is causal and stable. Okay. So then estimation of the power spectral density is amounts to estimating h e to the power j omega. What is this system? Because mod square of that times some constant. That constant will be the variance of this. That can be separately estimated, or even if you do not know that, it is just a scaling parameter. It will not change the shape of the PSD. Absolute value it might change, the shape will not be changed, right? So, basically it amounts to identification of the system, it becomes a system identification problem. Then in parametric estimation, what do? We have to then introduce some approximation. In one approximation, you say that Hn is an impulse response of a model of a rational system, that is parametric spectrum estimation. Hn you assume to be impulse response of rational system. I do not know whether you know rational systems. You have all studied in DSP. It is called constant coefficient difference equation with zero initial condition. I do not know how well it has been taught in DSP, but in a constant coefficient difference equation, if you do not have zero initial condition, it does not become linear and time invariant firstly. You have to have zero initial condition. Some other day I will discuss offline, not along this course. Rational system means Hz is approximated as that is modeled as this kind of form. It was a general Hn. Up to this it was accurate because old gave us this. This is always true. But old never said that this Hn actually, if you take the Z transform of Hn, you will get a closed form like this. This is something we are introducing. We are saying that by taking Q and P, the two orders to be very large, we will approximate actual Hz by something like this. This model, if you take the model as it is with both numerator and denominator, then it has got zeros also, poles also. It will be called a pole zero model. Pole zero model is also called. In that case, if you have a model like this, then we simply need to find out. Here I had to find out all the infinite coefficients H0, H1, H2, H3, dot dot up to H infinity. Then only I can find out H to the power j omega. But here the advantage is you need to find out only these coefficients B0, B1 up to BQ and A1 to AP. If you somehow estimate these coefficients, transfer function is known. So entire infinitely long impulse response is basically captured by a few finite number of coefficients. So your entire purpose is turns out to be what? From a given data record of the process Xn, somehow estimate by some technique, estimate B0, B1, BQ and A1 to AP. If you can estimate them, then find out H to the power j omega mod square of that times some scaling constant will be the PSD. That is what is called parametric power spectral estimation. These parameters need to be estimated. So entire thing turns out to be what? Find out better and still better technique by which you can estimate B0 to BQ and A1 to AP. Entire power spectral density estimation amounts to that, plus the input variance to be absolutely accurate. Okay, you understand? Here, if you assume the model to be just like this, both zeros and poles present, there is called a pole zero model. Pole zero model also called autoregressive moving average, ARMA, autoregressive moving average model. That is the difference equation will be what? If it is yz will be what? Output is xn, input is un. So, there will be xn output plus okay. This should be u, sorry. Input u, output x. Mind you, this kind of things, just writing this is not enough. You have to have zero initial condition. That comes from DSP, that we will not discuss here. Please understand, in the case of differential equation in continuous time system, you have to ensure zero initial condition, then only it becomes linear and time invariant. Then only output by input Laplace transform ratio turns out to be h of s, which is the Laplace transform of Hn, Ht. In this case, zero initial conditions you have to assume that when the switch system is switched on, all xn its past values xn minus 1 xn they are all 0, then only it can be shown separately. It is LTI. In that case, y xz by uz, xz by uz is always of this form, whether you have linear zero initial condition or not. But only when zero initial condition, xz by uz will turn out to be hz, because under zero initial condition it is LTI. For LTI system, output is nothing but convolution between the two in z domain, product of the two z transforms. So output z transform by input z transform turns out to be hz. So only, because I am telling you again, even when there is no zero initial condition, xz by uz will be this, but xz by uz will not then be hz. Is because it is not a linear time invariant system. So this is not a convolution, output is not a convolution between the two. So xz is not uz into hz, that can be shown separately. But only when if you ensure zero initial conditions, then I can prove separately, irrespective of all these, that it's a LTI system. For LTI system, output is a linear convolution between these two, which means z transform wise, output z transform by input z transform will be hz. So output z transform by input z transform, which takes this kind of form, will indeed be indicating the hz for the system. Okay. This is a separate story. If you have not studied in DSP, I am sure you have not studied. It is not given in books, and teacher of course will not teach it. I can very well foresee. It is not linear, not time invariant. What it has to? Unless you ensure that, even if you take this kind of form, xz. Yeah, otherwise not. Otherwise this modeling collapses. Anyway, pardon me? Oh, B0 into Vn, sorry, there is B0 into Vn, thank you. So this is called AR, this side is called the autoregressive part, regression on itself, xn, and the regression, na, xn minus 1, xn minus 3, regression, auto, regress on itself, that is autoregressive. This moving average, because this after all some kind of averaging, linear combination of un to n minus q. Okay, some kind of average, but average again changes from, because right now your leading coefficient, leading term is un, and you are averaging this term un up to un minus 1 and un minus q, but next time it could be un plus 1, then un. So this average is moving with time, changing with time. That is what we call moving average part, autoregressive moving average. Sometimes you can just take the model to be only this, as though denominator is only 1. This is a special case of ARMA, only moving average part, and that is called MA model, moving average model. In that case, if it is only 1, xn output, this part is not present, xn is just this. Remember, in both ARMA and MA, you solve basically to estimate B0 to BQ, you are basically looking at a non-linear problem. It is because input, you are only giving the data xn. You are only modeling it like this, you do not know which random sequence generated it. So un is unknown to you. But so are these coefficients B0 to BQ, and here you have a product of two unknowns. So whether it is MA model or ARMA model is basically a non-linear estimation procedure that makes life hell. But when it is this part, that suppose you take only this, only poles, numerator may be a coefficient B0, in that case you have got this term. It is an all pole model. It is a linear estimation problem, because on the left hand side parameters are unknown, but xn is known to you. This is the model which is a celebrated model, which has been studied most extensively. It is called autoregressive model, AR model. This B0 can be absorbed in un also, because if un is wide, so is B0, B0 into un. Okay, but we need to find out the variance of this overall process B0 into un, because output per spectral density will be not only mod square of this, but also that times input variance. Input is white, is variance. So B0 u into un, if you call it u prime n, I must know the variance of u prime n. Okay. So this autoregressive model we have considered. Okay. This B0 un I will be calling u prime n, or why even u prime n? If you permit, I will call it again by un only. First you call it u prime n, B0 un you call u prime n, and u prime n you call as un again, no problem. So that means what you have got, please see that there are two books on this, fantastic books, easy to read but celebrated books on spectral estimation by the professor and his student, teacher and student, each wrote separately. One is one is called modern spectral estimation by the professor, celebrated person, a wonderful man also, Stephen Kay, SMK. Modern, they are in the library. People who are doing research and all that have those kind of things in mind can even buy this book, or at least must have a look at this book. Modern spectral estimation by someone who is a great researcher in this area and also a great person. We know, so he is known to be a great person, really, SMK. And his PhD student who also became very famous, his name is Larry Marple. He wrote a book simultaneously, so the books are more or less overlapping. Each is great book by its own, but books have to be given defined names, you see. So then Marple gave this name digital spectral estimation. You know, both. I personally am more familiar with this Kay's book. By Larry L. Marple. Both are Prendisol books, both are there in the library, and not difficult to read. It does not assume any extra knowledge and anything. Very reader friendly kind of books.
There are 2 volumes of the first one?
No, to my knowledge. There may be 2 copies, but 1 volume. 2 copies maybe. Okay. MARPLE. Marple. So this is our problem. We are finding out this is the system 1 plus A1 sorry xn. So in time domain this is what, and UN is white, and I am assuming the model to be, most importantly, I am assuming the model to be causal and stable. Now see one thing before I proceed further. Suppose I am interested in the random process xn. After the random process, exact samples are not any consequence to me. It's power spectral density, that random, if I can generate a similar random process, that means something which is a similar statistical structure, statistical thing, that will be enough for me. Suppose xn represents your word, IIT, suppose. Every time you utter IIT, you will get different xn's, but they all have they all belong to the same statistical class. They are say power spectra and all, they will be same, isn't it? They belong to a statistic. So suppose instead of sending xn, what I do, I find out these parameters A1 to AP and the input variance. That's enough for me to generate the random process. Exact samples are not enough. I should generate that random sequence whose PSD is of that type. And then if I play it in a speaker, it will generate the word IIT. Okay, very loosely speaking. So that is actually basis for all this linear predictive coding and all that, you know, that instead of transmitting the entire block of xn, if it is relatively accurately can be modeled like this by an AR model, you better estimate A1 to AP and input variance and send them, that's all. So that's p plus 1 number of parameters. Okay, you don't need to sample send all the samples. Anyway, let's find out these equations. For the time being, let me permit to place permit B to let prime B here. Sorry, this will be a problem. And this has got impulse response Hn, which is causal and stable. Please see, I am assuming, because I will be deriving this model must be causal and stable, otherwise there is no point. That okay, I estimated a model and parameters turn out to be such, the poles lie outside unit circle, and therefore this is a causal and it's not a causal and stable system. Then this is no good, isn't it? System must be causal and stable. Then only all those formula remains valid, that okay, output power spectral density is mod this square times. If the system is not working, system is non-causal and stable, it will not work. It has to be a real life system, causal and stable. Okay. Now if it is causal and stable, that means what? This is a model equation, but parallelly xn is what? H0 into un plus h1 un minus 1 h2 un minus 2 plus dot 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 causal, that is why it is starting at H0, times current 1, then H1 times Un minus 1, H2 times Un minus 2. Okay. Then can I say that Un is orthogonal to xn minus k, k is 1, 2, dot, dot, dot. Say start with k equal to 1, xn minus 1. What is xn minus 1? It will depend on Un minus 1, Un minus 2, Un minus 3, dot, dot, dot. Un is white. So, Un correlation between Un to Un minus 1 or minus 2 or minus 3, minus 4, they are all 0. So, that means Un is orthogonal to xn minus 1, because after all if it is xn minus 1 here, it will depend on Un minus 1, minus 2, minus 3, like that. And current one is Un. So, Un is orthogonal to each of those terms, Un minus 1, Un minus 2, Un minus 3, that means Un is orthogonal to xn minus 1. By the same logic, Un is orthogonal to xn minus 2, xn minus 3, etc., etc. Okay. That means if I project Un on the space spanned by all the past Un minus 1, Un minus 2, dot, 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 space spanned by them, project Un on that, that projection will be 0, because it is already orthogonal. It is orthogonal, na? If it is already orthogonal, projection is 0, and it itself is the projection error. If suppose somebody is projected, that somebody is already orthogonal, then projection error is 0, isn't it? Now, suppose in this model, on the left hand side and right hand side, both I project on the space, say W only, which is span of or just a minute. No, I can make it simpler. Suppose left hand side and right hand side, I consider this space with which you are familiar. What is W1 comma P? It is span of, actually I am hurrying because of this signal I got that wind up. This is W1 comma P. Suppose left hand side I project on this, right hand side I project on this. Projections will be same, isn't it? But right hand side Un is orthogonal to xn minus 1, just now I have seen, because xn minus 1 depends on Un minus 1, then Un minus 2, all that. Un is orthogonal to xn minus 2 also, Un is orthogonal to xn minus p also. That means Un is orthogonal to this space, so projection is 0, isn't it? Projection is 0. So, right hand side becomes 0. On the left hand side, projection is a linear operation. So, overall projection is projection of xn on this plus projection of this on this, projection of next term on this, and so on and so. So, first one will be P1P xn. Okay, P1P, very quickly, I do not have time now. P1P xn. Then can you tell me what is the projection of A1 prime? A1 prime is forget what is the constant, xn minus 1 on this, xn minus 1 on, if you project xn minus 1 on W1 comma P. What is that projection? It itself, it is lying there. It is lying there. So, if you project that is the one which will give the minimum error. Error is 0 there. See, projection is 1 which gives rise to minimum error. Now, xn minus 1 is such that the error between xn minus 1 and xn minus 1 is 0. Okay. Same for others. So, you see, right? That means what is the projection? Projection is, if I take minus here, this. Now, can you see? But this projection, now consider linear prediction. Xn projected on this means it is a linear combination of those terms, that is minus AP1 AP P so you can identify easily these coefficients. These coefficients are the predictor coefficients. That means if there is an AR model satisfied, AR model coefficients are nothing but the corresponding pth order linear prediction coefficients. They turn out to be same. I stop here today. Next class again I will continue from here. I just, because I do not know how much it went through. Actually, this relates linear prediction to AR modeling. Okay, that is all for